Bismillahirrahmanirrahim. Hello students, welcome to the electrical engineering channel. In this lecture, I am going to discuss another rule of numerical integration, and that is called Gauss quadrature rule of integration. And according to this integration, the integration of any mathematical function can be actually expressed in the form of linear combination of f of a and f of b, right? So f of a is the value of the function at the lower limit of integration, and f of b is the value of the function at the upper limit of the integration. So this integration or this definite integration is equal to c1 f of a plus c2 f of b. So f of x can either be considered as a first order polynomial or a second order polynomial. So, as was the case with the Simpson's rules, we have to consider the function equivalent to the polynomial expression. So, if we consider the function as approximated to the first order polynomial, then this Gauss quadrature rule of integration will be much simpler. Okay, so f of x is equal to a naught plus a1x, and the integration of this function for these limits from a to b can be written as a naught b minus a plus a1 b square minus a square over 2, and that integration is equal to c1 f of a plus c2 f of b, and f of a is equal to a naught plus a1 a, f of b is equal to a naught plus a1 b, and put these expressions here, and this can be rearranged, and a naught can be taken as common, so it will become a naught into c1 plus c2 plus a1 into c1 a plus c2b. So we can compare the coefficients or multipliers of a naught and a1 at the right hand side and at the left hand side. So it means c1 plus c2 is equal to b minus a, and c1a plus c2b is equal to this expression. So here we have two unknowns, C1 and C2, and these two equations can be written in the matrix form. And after writing these equations in the matrix form, we can evaluate C1 and C2 by either using Cramer's rule. So C1 is equal to B minus A by 2, and C2 is also equal to B minus A by 2. So by putting these values in this expression, C1 and C2, these are the only unknowns, we can evaluate this integration. So that integration is quite simpler. Okay, so this integration will be equal to b minus a by 2 f of a plus b minus a by 2 f of b. So we can also use two-point Gauss quadrature rule, and for this method we have to approximate our polynomial as a third order polynomial. Okay, so in this case, this is our integration, and it is equal to c1 f of x1 plus c2 f of x2. So here we have four unknowns, c1 x1 c2 x2, and we have to consider a third order polynomial, and here we will have four coefficients a naught, a1, a2, and a3. Okay, so the integration of this third order polynomial is equal to this expression, and this is equal to c1 f of x1 plus c2 f of x2. Now this can be written as c1 f of x1. Okay, so f of x1 is equal to a naught plus a1 x1 plus a2 x1 square plus a3 x1 cube, and c2 f of x2, so it will be c2, and this is f of x2, the value of the function at x equal to x2. So this equation can be rearranged, and after rearranging, we can write this whole equation as this. So we can take a naught as common, and we will have c1 plus c2 over here plus a1 into c1 x1 plus c2 x2 plus a2 into this expression plus a3 into this expression. Now this equation can be compared with this equation 1 number 1, and by this comparison we can say that c1 plus c2 is equal to b minus a, c1 x1 plus c2 x2 is equal to b square minus a square divided by 2. Similarly, this expression will be equal to this expression, and this expression is equal to this expression. Now we have four equations, and we have four unknowns, c1, c2, x1, and x2. So you can observe that first two equations this one and this one, they are exactly the same as we obtained for this Gauss quadrature rule, in which we used the first order polynomial approximation. So it means we will get the same values of C1 and C2 as we did before. Okay, so C1 and C2 will be same and they are equal to B minus A by 2. So the other two unknowns X1 and S2 can also be evaluated by solving these four equations simultaneously. So this can be done by either using MATLAB, the symbolic math toolbox as we did for Simpson's rules, and these unknown values are also written over here. So x1 is equal to b minus a by 2 minus 1 by square root 3 plus b plus a by 2, and x2 is equal to b minus a by 2 1 by under root 3 plus b plus a by 2. So these are the four unknowns, and after evaluating their values, we can use these values in this expression c1 f of x1 plus c2 f of x2. So this integration can also be evaluated quite easily by using this numerical method, which is called two-point Gauss quadrature rule. So this method will give a more accurate result, and this method will also give a good result, but its accuracy will be smaller. So I hope you have understood the contents of this lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.